Hello and welcome back. I'm glad you found your way here again tonight. Tonight we're stepping back even further than usual, beyond the sun, beyond the planets, beyond the edges of our own solar system entirely, to look at the vast, glowing structure that holds all of it together, the Milky Way, our home galaxy. It's the closest thing we have to an address in the universe, and tonight we'll drift slowly through its spiral arms, its ancient core, and its quiet, star-filled distances. If this is your first time here, consider subscribing to Drowsy with Facts, where every episode is 100 gentle facts, softly narrated, designed to carry you all the way to sleep. For now, let's begin. It helps, before we go any further, to understand simply what a galaxy actually is. A galaxy is an enormous, gravitationally bound collection of stars, gas, dust, and dark matter, all orbiting a shared center. Our galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars, a number so large that even astronomers describe it as an estimate rather than a precise count, because so many of those stars are simply too faint, too distant, or too obscured by dust to be individually observed. Alongside all those stars, the Milky Way is also home to countless planets, moons, nebulae, and vast, mostly empty stretches of interstellar space, all held together by gravity across a disk that spans roughly 100,000 light years from edge to edge. That number is worth sitting with for a moment, because it's almost impossible to picture. A single light year is the distance light travels in 1 year, moving at roughly 6 trillion miles every 12 months. So when we say the Milky Way is 100,000 light years across, we mean that light itself, the fastest thing in the universe, would need 100,000 years just to cross from one side of our galaxy to the other. Our own sun takes about 230 million years to complete a single orbit around the galaxy's center, a span of time so long that the last time our solar system was in its current position, dinosaurs hadn't yet appeared on Earth. The Milky Way is classified as a barred spiral galaxy, meaning it has a central, elongated bar-shaped structure of stars, with graceful spiral arms curving outward from either end of that bar like a great pinwheel slowly turning in the dark. From above, if we could somehow view it from outside, which we can't since we're embedded within it, the Milky Way would look remarkably similar to many of the other spiral galaxies astronomers have photographed throughout the universe, with sweeping arms of bright young stars and glowing pink nebulae tracing delicate patterns against a background of older, dimmer starlight. We happen to live inside one of these spiral arms called the Orion Arm, sometimes referred to as the Orion Spur, a relatively minor structure compared to the two major arms of the galaxy, the Scutum Centaurus Arm and the Perseus Arm. Our position within this smaller arm, roughly 26,000 light years from the galaxy's center, places us in a quiet, relatively uncrowded region of the Milky Way. Not at the heart of the action, but comfortably tucked into one of its gentler, outer neighborhoods, drifting slowly along with the rest of our local stellar surroundings. At the very center of the Milky Way lies something extraordinary, a supermassive black hole named Sagittarius A star, with a mass roughly 4 million times that of our sun, compressed into a region of space not much larger than our solar system. For a long time, the existence of this object was inferred only indirectly, through the strange, rapid orbits of stars swinging incredibly close to the galactic center. moving so fast and so tightly that only an immense invisible mass could explain their behavior. Then in 2022, astronomers achieved something remarkable. They captured the first ever direct image of Sagittarius A star using a network of telescopes spread across the entire planet, working together as one enormous Earth-sized instrument, finally allowing us to see, however faintly, the dark silhouette of the object anchoring our entire galaxy in place. It's worth pausing on just how strange this is to think about. That everything in the Milky Way, every star, every planet, every quiet corner of space we've ever explored, is slowly, patiently orbiting an invisible monster at the center of it all. One so dense that not even light can escape its pull once it crosses a certain boundary. And yet from our comfortable position out in the Orion Arm, 26,000 light years away, that black hole poses no danger to us at all. It simply sits there, quietly anchoring the galaxy, doing what it has likely done for billions of years, while we drift along in our own small, peaceful orbit, far from its immediate influence. The Milky Way itself is thought to be roughly 13.5 billion years old, meaning it began forming not long after the universe itself came into existence, in the earliest chapters of cosmic history. Its formation likely began with the gradual collapse of a vast cloud of primordial gas, left over from the early universe, which slowly clumped together under its own gravity, giving rise to the first generations of stars. Over billions of years, the Milky Way grew larger, not just by forming new stars internally, but by merging with and absorbing smaller neighboring galaxies, a slow, ongoing process of cosmic cannibalism that astronomers can still trace today through streams of stars in our galaxy's outer regions that show telltale signs of once having belonged to a separate, smaller galaxy entirely. One particularly well-studied example of this is the Sagittarius dwarf galaxy, a small companion galaxy that has been slowly torn apart and absorbed by the Milky Way's much stronger gravity over the past several billion years. Its stars are gradually being pulled into a long, looping stream that wraps around our galaxy. And some of those stars, originally born in a completely different galaxy altogether, have likely already been folded into our own galactic disk, quietly mixed in among stars that formed here at home. An invisible reminder that the Milky Way's history is one of steady, patient absorption, rather than isolated, quiet growth. Our sun, along with its family of planets, sits in a relatively calm and stable region of the galactic disk, and it's worth spending a little time on the sun's own journey through the Milky Way, since it's a journey we're all quietly taking part in right now. As the sun orbits the galactic center, it also gently bobs up and down through the flat plane of the galactic disk, oscillating above and below it roughly every 30 million years or so, like a slow, cosmic breathing motion. Some scientists have speculated, though it remains a topic of ongoing research and debate, that these oscillations might occasionally expose our solar system to slightly different regions of interstellar space with varying levels of cosmic radiation, and that this could, over very long timescales, correlate with patterns in Earth's own geological and biological history. The Milky Way is not alone in the universe, of course, and it exists as part of a small cluster of galaxies called the Local Group, which contains roughly 80 known galaxies of varying sizes, held together by their mutual gravity across a region of space several million light years wide. The two largest members of this group are the Milky Way and the Andromeda Galaxy, our nearest large galactic neighbor, sitting at a distance of about 2.5 million light years away. Close in cosmic terms, but still almost unimaginably far by any human measure. Andromeda is visible to the naked eye on a sufficiently dark, clear night, appearing as a faint, fuzzy smudge of light, and it holds a particularly interesting distinction. It is, remarkably, the most distant object visible to the unaided human eye, meaning that when you look at it, the light entering your eyes left that galaxy 2.5 million years ago, long before modern humans existed on Earth at all. Andromeda is also, by most estimates, somewhat larger than the Milky Way, though recent research suggests the two galaxies may actually be more comparable in total mass than once believed, once the contribution of dark matter is properly accounted for. And Andromeda and the Milky Way share more than just a neighborhood. They're on a slow, inevitable collision course with one another. The two galaxies are approaching each other at a speed of roughly 250,000 miles per hour, and in approximately 4.5 billion years, they're expected to collide and eventually merge into a single, much larger galaxy, sometimes nicknamed Milkomeda by astronomers in anticipation of that distant future event. Despite the dramatic sound of two galaxies colliding, the actual stars within them are spaced so incredibly far apart that direct collisions between individual stars are expected to be exceedingly rare. It will be, in a sense, a quiet, graceful merging of vast structures rather than a violent, star-shattering crash. The Milky Way also has a number of smaller companion galaxies of its own, orbiting it much like moons orbit a planet, though on a far grander scale. The Large Magellanic Cloud and Small Magellanic Cloud are two of the most notable, visible from the southern hemisphere as faint, glowing patches in the night sky, named after the explorer Ferdinand Magellan, whose crew documented them during their historic voyage in the 16th century. These smaller galaxies are gradually being pulled apart by the Milky Way's gravity as well, slowly feeding fresh gas and occasionally new stars into our galaxy's outer regions, a quiet ongoing exchange between our galaxy and its smaller neighbors. Within the Milky Way itself, stars are born continuously in vast stellar nurseries called nebulae, enormous clouds of gas and dust where gravity slowly pulls material together into dense clumps, eventually growing hot and dense enough at their cores to ignite nuclear fusion and become new stars. The Orion Nebula, visible even with a modest backyard telescope, is one of the closest and most well-studied of these stellar nurseries. A glowing pink-tinged cloud where thousands of new stars are currently in various stages of formation, some barely a few 100,000 years old. Infants by stellar standards, in a galaxy where many stars live for billions of years. Not all stars in the Milky Way are young, of course. Some of the oldest stars ever discovered are found in structures called globular clusters, tightly packed spherical groupings of stars, sometimes containing hundreds of thousands of individual stars, bound closely together by gravity, orbiting the Milky Way's center in wide, looping paths that carry them above and below the main galactic disk. These globular clusters are thought to be among the oldest structures in the entire galaxy, with some containing stars that formed not long after the Milky Way itself began coming together, more than 13 billion years ago. Ancient survivors that have watched the rest of the galaxy slowly grow and change around them. The Milky Way's disk isn't uniformly flat either. Astronomers have discovered that the outer regions of our galaxy's disk are actually gently warped, curving upward on one side and downward on the other, somewhat like a subtly bent vinyl record rather than a perfectly flat plane. This warping is thought to be caused by the gravitational influence of the Milky Way's satellite galaxies, particularly the Large Magellanic Cloud, tugging at the outer edges of our galaxy's disk as it orbits, gradually distorting its shape over long stretches of cosmic time. Surrounding the visible disk of stars, gas, and dust, the Milky Way is enveloped in a much larger, much less understood structure called a dark matter halo. Dark matter itself remains one of the most persistent mysteries in modern astronomy. It doesn't emit, absorb, or reflect light, making it entirely invisible to any of our telescopes. And yet its gravitational influence is unmistakable, revealed through the way it affects the motion of visible stars and gas throughout the galaxy. Without the extra gravitational pull provided by this invisible dark matter, the outer stars of the Milky Way would be moving far too quickly to remain gravitationally bound to the galaxy at all. By all conventional accounting of visible matter alone, they should simply fly off into intergalactic space. Instead, they remain steadily in orbit, held in place by something we still cannot directly see or fully explain. It's worth remembering, too, that from our vantage point here on Earth, we only ever see a portion of the Milky Way directly. The hazy, glowing band of light that stretches across a truly dark night sky, made up of the combined glow of countless individual stars, too faint and too numerous to distinguish one from another with the naked eye. This band represents our edge-on view into the galactic disk, looking inward toward the crowded, star-dense plane of the galaxy from our own position, embedded within one of its outer arms. In areas with significant light pollution, this faint band has become almost entirely invisible to most people today. A quiet reminder of how much of the night sky has slowly been lost to artificial light over the past century, even as our understanding of what lies beyond it has grown deeper than ever before. The very name Milky Way has ancient roots, tracing back to Greek mythology, where the pale band of light across the night sky was imagined as a trail of spilled milk associated with the goddess Hera. The Latin phrase Via Lactea, meaning Milky Road, eventually gave rise to the English name we still use today. Cultures across the world, long before telescopes existed, developed their own rich stories and interpretations of that same glowing band overhead. Some saw a river of stars, others a path for the souls of the dead, and still others a great cosmic road connecting the heavens to the earth. Each culture quietly reaching for language to describe the same distant, glowing structure we now understand to be our own galaxy viewed from within. Let's drift now through a few more of the individual wonders scattered throughout our galaxy's vast structure, tucked among its spiral arms and ancient star clusters. Scattered throughout the Milky Way are stellar remnants of a very different kind. Neutron stars, the incredibly dense, collapsed cores left behind after a massive star explodes in a supernova. A neutron star can pack more mass than our entire sun into a sphere only about 12 miles across, so dense that a single teaspoon of its material would weigh roughly 1 billion tons here on Earth. Some neutron stars spin incredibly rapidly, sweeping beams of radiation around like a cosmic lighthouse as they rotate. And these are known as pulsars, first discovered in 1967 when astronomers detected a strange, remarkably regular pulse of radio waves that, for a brief and excited moment, some researchers wondered might be a signal from an alien civilization before the true natural explanation was understood. Scattered throughout the galaxy as well are the remnants of supernovae themselves, the explosive deaths of massive stars which briefly outshine entire galaxies before fading, leaving behind expanding shells of gas and dust that slowly disperse back into the interstellar medium over thousands of years. The Crab Nebula, one of the most famous supernova remnants in the Milky Way, is the visible aftermath of a supernova explosion recorded by astronomers in China and elsewhere in the year 1054. An event so bright that it was reportedly visible in daylight for weeks. At the center of that expanding cloud of debris lies a pulsar, spinning about 30 times every second, a quiet, rapidly rotating relic of the massive star that once occupied that same patch of sky nearly 1,000 years ago. Astronomers often describe the stars of the Milky Way as belonging to two broad populations, a distinction that turns out to reveal a great deal about the galaxy's long history. Population 1 stars are relatively young, metal-rich stars. Metal, in astronomical terms, meaning any element heavier than hydrogen and helium. And they're found concentrated in the spiral arms and disk of the galaxy, including our own sun. These stars formed from gas that had already been enriched by the deaths of earlier generations of stars, since heavier elements are forged in stellar cores and scattered into space through supernova explosions. Population 2 stars, by contrast, are older, metal-poor stars, largely found in the galaxy's central bulge and its globular clusters, having formed much earlier in the Milky Way's history, before successive generations of stellar deaths had a chance to enrich the surrounding gas with heavier elements. In a very real sense, our own sun, and every planet orbiting it, is made partly from the recycled remains of earlier stars that lived and died long before the solar system ever existed. A quiet inheritance passed down through billions of years of stellar life and death. Between the stars themselves lies the interstellar medium, a thin, mostly empty expanse of gas and dust that fills the space throughout the galaxy, far less dense than even the best laboratory vacuum achievable on Earth, and yet still substantial enough across such vast distances to shape entire regions of the galaxy. This interstellar medium isn't spread evenly. In some places, it gathers into dense, cold molecular clouds, the raw material from which new stars eventually form, while in other regions, it exists as hot, thin, ionized gas, heated by the intense radiation and shock waves from nearby massive stars and supernova explosions. Some of these molecular clouds are so large and so dense with dust that they block visible light almost entirely, creating dark patches against the brighter background of the galaxy. Regions early astronomers once mistook for genuine gaps or holes in the star field, before realizing they were simply looking at dense clouds of obscuring dust rather than true empty space. One particularly striking example of this effect is a region sometimes called the Great Rift, a long, dark lane of dust that appears to split the bright band of the Milky Way in two when viewed from a sufficiently dark sky, stretching across a huge portion of the visible galaxy. For a long time, various cultures around the world incorporated this dark, winding shape into their own sky lore, sometimes describing it as a great serpent or a dark river running alongside the brighter star-filled band. An entire second landmark hidden in plain sight, formed not by stars themselves, but by the absence of visible starlight behind a curtain of interstellar dust. Mapping the structure of the Milky Way has always presented a peculiar challenge, precisely because we are embedded inside it, rather than viewing it from some comfortable vantage point far outside its disk. Astronomers can't simply take a photograph of the whole galaxy the way we can with more distant galaxies like Andromeda. Instead, our understanding of the Milky Way's spiral structure has been pieced together slowly over decades, using indirect methods, carefully measuring the distances and velocities of stars and gas clouds throughout the galaxy, and using radio telescopes to trace the distribution of hydrogen gas, which glows faintly at a specific radio wavelength regardless of visible light or obscuring dust. It's a bit like trying to understand the layout of an enormous, sprawling city while standing inside one particular room, gradually building up a mental map through careful, patient measurement, rather than ever simply stepping outside to see the whole structure laid out at once. The spiral arms themselves are thought to be shaped, at least in part, by something called a density wave. Not a fixed physical structure that individual stars remain locked into forever, but rather a slow-moving pattern of gravitational compression that sweeps through the galactic disk, somewhat like a traffic jam moving along a highway. Individual stars pass into and out of the spiral arms over time as they orbit the galactic center, briefly slowing down and bunching together as they pass through this wave of higher density, before continuing on their way and gradually spreading back out again. Our own sun has likely drifted into and out of different spiral arms many times over its long orbital history, spending some stretches of its multi-100-million-year orbit within the bright, crowded structure of a spiral arm, and other stretches out in the quieter, more sparsely populated space between them. The Milky Way is also home to a strange and only relatively recently discovered structure called the Fermi bubbles. Two enormous, symmetrical lobes of gamma ray and X-ray, emitting gas extending far above and below the galactic center, first identified in 2010, using data from NASA's Fermi Gamma Ray Space Telescope. Each bubble stretches roughly 25,000 light-years from the galactic plane, and together they represent one of the largest structures ever discovered in our galaxy. Their exact origin remains a topic of active research, though many astronomers suspect they were formed by a period of intense activity from Sagittarius A star, perhaps a few million years ago, when the supermassive black hole at our galaxy's center may have been considerably more active than it appears to be today, blasting enormous jets of energetic particles outward in a burst that left these ghostly, glowing structures towering above and below the rest of the galaxy. It's worth remembering, too, that the Milky Way itself, vast as it feels to us, is only a small part of a much larger cosmic structure. Our local group of galaxies containing the Milky Way Andromeda and dozens of smaller companions, is itself just one small cluster within an even larger structure called the Laniakea supercluster, a vast collection of over 100,000 galaxies spanning roughly 500 million light years, all gently flowing together under their mutual gravitational influence, like a slow cosmic river carrying entire galaxies along with its current. The name Laniakea comes from Hawaiian, meaning immeasurable heaven, chosen specifically because the discovery of this vast structure was led by researchers connected to Hawaii, where some of the world's most powerful telescopes are located, quietly measuring the movements of galaxies far beyond anything visible to the naked eye. Scattered among the hundreds of billions of stars in the Milky Way, astronomers now believe that planets are not rare exceptions, but rather the norm. Since the first confirmed detection of a planet orbiting another sun-like star in 1995, the pace of discovery has accelerated dramatically, and thousands of exoplanets have now been confirmed throughout our galaxy, with statistical estimates suggesting that, on average, most stars in the Milky Way likely host at least one planet of their own. Many of these worlds have been discovered using a method called the transit technique, which involves patiently watching a distant star for the tiny, telltale dimming that occurs when a planet passes directly in front of it from our point of view, blocking a small fraction of its light. Missions like NASA's Kepler Space Telescope spent years staring fixedly at a single patch of sky, monitoring hundreds of thousands of stars simultaneously, quietly cataloging thousands of new worlds hidden throughout our galaxy, each one a small, distant echo of our own solar system. Threaded throughout the Milky Way's vast structure is also a pervasive, if largely invisible, galactic magnetic field generated by the complex motion of charged particles and ionized gas throughout the galaxy. This magnetic field, though far weaker than a simple refrigerator magnet here on Earth, stretches across such enormous distances that it plays a significant role in shaping the galaxy structure, influencing the formation of stars within molecular clouds, and helping to guide the paths of cosmic rays, extremely high-energy particles, mostly protons, that streak through the galaxy at speeds approaching the speed of light. Some of these cosmic rays originate from the violent aftermath of supernova explosions, accelerated to tremendous energies by the expanding shock waves those explosions produce, before eventually scattering throughout the galaxy, occasionally reaching all the way to Earth, where they continue to strike our planet's upper atmosphere, even now tonight, in a steady, mostly unnoticed rain of high-energy particles from across the galaxy. It's worth taking a slow, unhurried look, too, at how researchers have come to understand the sheer scale of star formation happening throughout the Milky Way at any given moment. Despite containing hundreds of billions of existing stars, the galaxy continues to form new ones at a steady, if modest, pace. Astronomers estimate that the Milky Way produces roughly 1 to 2 new stars, on average, each year, primarily within the dense molecular clouds scattered throughout its spiral arms. This might sound like a slow rate for a galaxy so vast, and in truth, it is considerably slower than it once was. Observations suggest that the Milky Way's star formation rate was significantly higher billions of years ago during the galaxy's early history, and has been gradually declining ever since, as the available reservoirs of dense star-forming gas are slowly consumed and not fully replenished at the same rate they once were. Looking ahead, far beyond even the eventual collision with Andromeda, billions of years from now, astronomers have begun to piece together a broader picture of the Milky Way's long-term future. As the galaxy continues to slowly consume its remaining reservoirs of star-forming gas, and as its satellite galaxies like the Magellanic Clouds are gradually torn apart and absorbed, the overall rate of new star formation is expected to continue declining. Eventually, following its eventual merger with Andromeda, the resulting combined galaxy is expected to settle over a very long time scale into a smoother, more uniform, elliptical shape, gradually losing the crisp, elegant spiral structure that defines the Milky Way today. A slow, graceful transformation, unfolding over a timescale so vast that it renders any human concern about it essentially meaningless. A quiet reminder of just how much time our galaxy still has ahead of it. It's worth taking a little time, too, to appreciate how recently we came to understand any of this at all. Since for most of human history, the true nature of the Milky Way remained a complete mystery. Ancient observers simply saw a faint, hazy band of light stretching across the darkest skies with no way of knowing what it actually was. It wasn't until 1610 when Galileo Galilei turned one of the very first telescopes toward that pale band of light that anyone realized the Milky Way wasn't a smooth, continuous cloud at all, but was instead made up of countless individual, faint stars, too numerous and too close together to distinguish with the naked eye. A discovery that quietly reshaped how people understood the night sky forever. More than a century later, the astronomer William Herschel attempted one of the first systematic efforts to map the actual shape of our galaxy, carefully counting stars in different directions across the sky and using those counts to estimate the galaxy's overall structure. His resulting map was reasonably close in some respects, though he significantly underestimated the galaxy's true size and placed our sun much closer to the center than we now know it actually sits. An understandable error, given that interstellar dust obscures our view toward the galactic center far more than astronomers of his era could have accounted for. It wasn't until the early 20th century that our true position within the galaxy became clear, largely thanks to the work of the astronomer Harlow Shapley, who carefully measured the distances to globular clusters scattered throughout the galaxy, using a newly developed technique involving a particular type of pulsating star called a Cepheid variable, whose brightness rises and falls in a precise, predictable rhythm directly related to its true luminosity. By mapping the distribution of these distant globular clusters, Shapley realized that they formed a roughly spherical halo centered not on our sun's position at all, but on a point far off in the direction of the constellation Sagittarius, finally revealing that our solar system was not, as long assumed, anywhere near the center of the galaxy, but was instead tucked away in its quiet outer reaches. Around this same period, one of the great scientific debates of the 20th century unfolded, sometimes referred to simply as the Great Debate, centered on a deceptively simple question. Were the faint spiral-shaped smudges of light that astronomers had observed scattered across the sky, called spiral nebulae at the time, actually relatively small, nearby objects contained within our own Milky Way? Or were they instead entirely separate galaxies in their own right, each containing billions of stars, positioned at almost unimaginable distances beyond our own. The question was finally settled in the 1920s by the astronomer Edwin Hubble, who used the same Cepheid variable technique to measure the distance to the Andromeda spiral nebula, discovering that it lay far, far beyond the known boundaries of the Milky Way. In doing so, Hubble didn't just settle a debate. He revealed essentially overnight that the universe was vastly larger than anyone had previously imagined, filled with countless separate galaxies, each one its own island of stars, with our own Milky Way now understood for the first time as simply one galaxy among many, rather than the entirety of the cosmos itself. Near the crowded, dust-obscured region surrounding the galactic center lies a particularly massive molecular cloud complex known as Sagittarius B2, one of the largest and most chemically rich star-forming regions anywhere in the Milky Way. Within this vast cloud, astronomers using radio telescopes have detected dozens of different complex molecules drifting through the cold, dark gas, including simple sugars and other organic compounds. Not evidence of life itself, but a quiet reminder that the fundamental chemical building blocks associated with living systems appear to form naturally and fairly commonly within the dense, star-forming clouds scattered throughout our galaxy. It's also worth remembering that most stars in the Milky Way don't exist entirely alone, the way our own sun does. A substantial fraction of the galaxy's stars are found in binary or multiple star systems, two or more stars gravitationally bound together, orbiting a shared center of mass, sometimes separated by distances comparable to our own solar system, and other times orbiting so closely that their outer atmospheres nearly touch. From a planet orbiting within such a system, an observer might witness something no one on Earth ever will: the gentle rise and fall of two or more suns crossing the sky together, casting overlapping shadows across an alien landscape. A quiet, strange kind of daylight, built from more than one star's worth of warmth. Beyond the visible disk of stars we've spent most of tonight exploring, the Milky Way is also surrounded by a much larger, sparser region called the galactic halo, a roughly spherical volume of space extending far above and below the flattened disk, populated by scattered old stars, globular clusters, and faint streams of stars left behind from smaller galaxies that were slowly torn apart and absorbed over billions of years, much like the Sagittarius dwarf galaxy we spoke of earlier. Astronomers have identified dozens of these faint stellar streams threading through the halo, each one a ghostly remnant of some long-vanished smaller galaxy, its stars now scattered along a wide, looping arc that traces the exact path of its slow gravitational unraveling. Piecing together these streams has become one of the more delicate detective stories in modern astronomy, allowing researchers to reconstruct fragments of the Milky Way's ancient history, one faint scattered trail of stars at a time, slowly revealing just how many smaller galaxies our own has quietly absorbed over its long, patient lifetime. It's worth returning one more time to that slow, sweeping orbit our entire solar system is quietly making around the galactic center, since it offers one last useful way of holding the Milky Way's true scale in mind before we let it go for the night. That single orbit, roughly 230 million years long, is sometimes called a galactic year, and it provides a strange, oddly humbling yardstick for measuring deep time. Our solar system has completed only about 20 galactic years since it first formed, some 4.5 billion years ago. The last time our sun and its planets were in roughly this same position along their orbit, the earliest dinosaurs were just beginning to appear on Earth, and the continents themselves were arranged in an entirely different configuration than the one we'd recognize today. 2 galactic years ago, complex multicellular life had barely begun to take hold in Earth's oceans at all. It's a slow, patient clock, ticking along far beneath our notice, entirely indifferent to the comparatively brief flicker of human history unfolding on the small, quiet planet drifting along with it. Some researchers have gone further still, exploring whether this long galactic orbit might have left any subtle imprint on Earth's own history, beyond simply providing a convenient measure of time. As our solar system moves through the galaxy, it periodically passes through regions of varying gas density, including the spiral arms themselves, where higher concentrations of gas and dust, and correspondingly higher rates of nearby supernova explosions could, in principle, expose our solar system to elevated levels of cosmic radiation for extended stretches of time. A handful of studies have proposed possible, tentative correlations between these galactic passages and long-term patterns in Earth's climate or its fossil record, though this remains a topic of ongoing scientific debate rather than settled fact. One small thread among many, connecting the vast, patient rhythms of the galaxy to the quieter, more immediate rhythms of life unfolding on the planet we call home. As we drift toward the end of tonight's journey, let's take one last slow pass back through everything we've traveled through together. We began by understanding what a galaxy even is: an enormous, gravitationally bound gathering of stars, gas, and dust, and learned that our own galaxy holds somewhere between 100 and 400 billion stars, spread across a disk roughly 100,000 light years wide. We found ourselves tucked into the Orion Arm, a quiet outer neighborhood of the galaxy, slowly orbiting a supermassive black hole at the galactic center that we only recently managed to photograph directly for the very first time. We trace the Milky Way's long, patient history of growth through mergers with smaller galaxies like the Sagittarius dwarf, and looked ahead toward its distant future, a slow, graceful collision with the Andromeda Galaxy, still billions of years away. We drifted through glowing stellar nurseries where new stars are born, and past ancient globular clusters holding some of the oldest stars in the entire galaxy. We considered the vast, invisible halo of dark matter holding it all together, and the strange, dense remnants, neutron stars and pulsars, left behind by the most massive stars once they've reached the end of their long, brilliant lives. And so tonight, we leave the Milky Way exactly where it has always been: a vast, quiet spiral of stars, slowly turning in the dark, home to our own small sun and its family of planets. One tiny, tucked away corner of a galaxy so large that light itself takes 100,000 years just to cross it. There's something quietly comforting in that kind of scale, in knowing that no matter how large or overwhelming a single day might feel, we are all together, gently riding along on one small planet, orbiting one ordinary star, tucked into one modest arm of one vast, ancient galaxy, drifting slowly and patiently through the dark, the way it has been doing for billions of years, and the way it will likely keep doing for billions more. You've drifted tonight through the crowded, star-filled bar at the galaxy center, out along the spiral arms, past glowing nebulae where new stars are born, and through ancient clusters holding some of the oldest light in the sky. You've traveled further tonight than any of us ever could in waking life, and you've done it without ever leaving the comfort of where you're resting right now. Let it hold you now, the quiet, steady turning of our entire galaxy, spinning gently in the dark, asking nothing of you except to rest. Sleep well, and I'll see you next time for another 100 facts, drifting softly into sleep.